The Koi Pond and the Lake, a film about the intelligence bubble based on an essay by David Montgomery. It begins with a question small enough to fit in a living room and expensive enough to move markets. What kind of thing have we actually built? David Montgomery's essay starts in a living room with his daughter and his baby son. She throws a hard ball at her baby brother. It hits his head, and he cries. A few minutes later, she throws a beach ball. It bounces softly, and he laughs. His sister does not need a million examples of what just happened. One lived event is enough to change what she knows about the world. That tiny scene points at the question behind this film. Today's AI systems can describe what happened with the hard ball and the beach ball. They can explain impact, softness, surprise, and laughter. During normal use, though, the model itself is usually unchanged by the event. It can talk about learning from experience while running against a fixed internal snapshot. The market is valuing AI as if that snapshot is close to becoming a living learner. Chapter 1. The Pond and the Lake. The essay's central analogy is simple. Current AI is an engineered koi pond. Beautiful, expensive, carefully maintained, and valuable. Real general intelligence would look more like a living lake, fed by a watershed, changed by weather, filled with memory, consequence, and adaptation. The financial bubble lives in the space between those two systems. We have built impressive ponds. Investors are paying prices that assume a lake is arriving on schedule. A modern language model is built through training, which means adjusting its internal settings until it predicts patterns in huge amounts of text and other data. Those internal settings are called weights, numerical values that shape what the model will say next. After training, normal use runs against those fixed weights. A conversation may be saved in a chat history, but the underlying model usually has the same weights afterward that it had before. Most modern language models use a transformer, the architecture introduced in 2017. It reads text as tokens, small pieces such as word fragment or punctuation mark. Transformers became powerful because they can compare many parts of a sequence at once and learn which relationships matter. That architecture helped turn the pond into something astonishingly useful. It also made the pond expensive to build. The knowledge cutoff is the date after which a model's built-in training data does not include new facts. A model may still search the web, read uploaded files, or use tools, but those additions are outside the fixed model. They are more like notes placed beside the pond. The fish can swim around them during a session, and the system may appear current, but the underlying trained fish have not grown from that experience. Training data is the hose water of the pond. It arrives from outside: books, websites, code, images, transcripts, and other human-made records. The pond becomes richer as more water flows in and as the filtering improves. The water can be vast, useful, and carefully selected. It still comes from somewhere else. The pond does not have its own watershed feeding it every day through rain, soil, runoff, insects, seasons, and the accidents of a living world. RLHF means reinforcement learning from human feedback. People rate model outputs, and training nudges the model toward answers people preferred. In the koi pond analogy, RLHF is purchased nutrients. It can improve the pond. It can make the fish behave in ways humans reward. It also means the system is shaped by outside judgment, applied in batches, under controlled conditions. The feedback is useful, but it is still maintenance delivered from the edge. When current AI products appear to improve during use, much of that improvement comes from systems around the model. Search brings in fresh information. Memory notes store selected facts about the user. Retrieval systems fetch documents from a database. Patches and prompt rules steer behavior. These are real engineering gains. In the pond analogy, they are heaters, filters, shade cloth, sensors, and valves. The pond becomes better managed, while the core trained fish remain fixed. A lake has a different kind of life. It takes in rain and runoff. It stores history in sediment. Algae blooms, insects hatch, fish spawn, plants die back, and weather changes the chemistry. A living intelligence would need something like that continuous contact with the world. It would keep learning from new experience, carry consequences forward, and become shaped by the environment it inhabits. The lake is not simply a larger pond. It is a different system. Emergence means an ability appears in a complex system without being explicitly programmed in advance. Modern AI has shown forms of emergence as models scale, translation, coding, reasoning patterns, and unexpected combinations of skills. That matters. The pond has produced surprising behavior. The lake argument asks a narrower question. Can surprising behavior inside a fixed trained system become continuous adaptation through contact with the world? No one has publicly demonstrated a complete system that takes that step. Koi are ornamental carp bred for human approval. Their value comes from color, pattern, rarity, and the market humans built around them. Wild carp live under consequence. They survive predators, mud, winter, low oxygen, strange food, and changing water. That does not make koi worthless. A beautiful koi can be expensive for good reasons. The analogy is about what kind of pressure shaped the intelligence. Approval produces one kind of fish. Consequence produces another. Chapter 2. The price of the gap. The pond is real. Current AI systems write code, summarize documents, tutor students, draft images, search records, translate languages, and help people move faster through complex work. Companies are already finding places where fixed models plus tools are valuable. Skepticism about the bubble should not be confused with dismissal of the technology. A managed pond can be beautiful, productive, and profitable. The problem begins when its price assumes it has already become a self-sustaining lake. The investment bubble is the price paid for the missing transition. Data centers, chips, power contracts, and software companies can all be rational around today's pond, up to a point. The risk is that capital spending has started to assume a future lake. Models that learn continuously, absorb enterprise reality, automate far more work, and justify much larger revenue. The bubble is the financial gap between useful present systems and the self-maintaining intelligence investors hope will arrive. A strange thing happens in booms. People build docks before the water level is known. They build marinas for boats that may or may not arrive. In AI, the docks are data centers, substations, fiber routes, cooling loops, chip orders, and debt schedules. Some of that infrastructure will be useful under many futures. Some of it only works financially if the lake becomes deep enough, soon enough, to float the boats promised in the spreadsheet. The financial layer matters because infrastructure has clocks attached to it. Debt has interest payments. Data centers have power commitments. Chips depreciate as newer chips arrive. Revenue projections have dates. If the lake arrives late or arrives smaller than expected, the pond may still be useful while the financing breaks. That is how a technology can be real and a bubble can be real at the same time. Another fragile pattern is circular investment. A chip company invests in an AI company. The AI company uses capital to buy chips. A cloud provider finances capacity. The capacity supports reported demand. Each step can be legitimate on its own, but the circle becomes dangerous when everyone inside it depends on the same future revenue arriving. The pond keeps getting expanded because the lake is assumed to be near. Chapter 3. The search for the lake. The technical case for the lake is not empty. Researchers are working on many pieces of the gap. Some work tries to change the architecture. Some tries to let models adapt during a task. Some tries to build internal representations of the physical world. Some tries to distill stronger systems into smaller ones, teaching a small model from a larger model's answers. These pieces deserve attention because they are serious attempts to move beyond a frozen snapshot. A state space model, or SSM, is a model design that keeps a compressed running state as it processes information. Instead of comparing every token with every other token in the same transformer style, it carries forward a changing summary. Mamba is a prominent line of state space model research. This matters because a running state can be efficient for long sequences. Efficiency can help the pond scale. It does not by itself prove that the pond has become a lake. Test time training, often shortened to TTT, means methods that let a model adjust during a task, usually temporarily. The phrase sounds close to learning from experience, so the definition matters. In most versions, the model adapts within a bounded problem and then resets or keeps only limited changes. That can be powerful. It is one path toward systems that behave less like static snapshots. It is still a partial mechanism, not a public demonstration of continuous general intelligence. A world model is a system that learns an internal representation of how the physical world behaves. It tries to capture structure such as objects, movement, cause, space, and consequence. A value function is the part of a learning system that estimates which outcomes are better. Together, those ideas point toward agents that can predict, choose, and learn from what happens. That is much closer to the lake image than a text predictor alone. One of the loudest voices for this direction is Yann LeCun, a Turing Award winner and, for a decade, Meta's chief AI scientist.
I can pass the bar exam or solve equations and things like that, do pretty amazing things. But we don't have robots that can do what a cat can do. The understanding of the physical world of a cat is way superior to everything we can do with AI. So that tells you the physical world is just way more complicated than human language.
JEPA means Joint Embedding Predictive Architecture. It is Yann LeCun's approach to building internal world models that predict useful structure rather than only generating words or pixels. The idea is to learn compact representations of what matters in a scene and predict how those representations change. That is a serious research direction for moving from pattern imitation toward grounded understanding. It remains one piece of a larger architecture that would still need memory, goals, feedback, and adaptation. The personnel moves around AI research have become part of the market story. Ilya Sutskever, OpenAI's former chief scientist, left and started Safe Superintelligence, often called SSI, a lab focused on building safer advanced intelligence. Yann LeCun has argued for world model approaches and has been reported moving toward new work outside Meta. Fei Li, who built the dataset that launched modern computer vision, now points her world labs at spatial intelligence, AI systems that understand three-dimensional environments. These are signals that serious researchers see unfinished architecture ahead.
I think the shelf life of the current paradigm, large language model, is fairly short, probably 3 to 5 years. I think within 5 years, nobody in their right mind would use them anymore, at least not as kind of the central component of an AI system. One analogy that some people have made, which I've recycled, is LLMs are good at manipulating language, but not at thinking. Okay.
Chapter 4, the case for the build-out. The strongest case for today's build-out is that a rough lake architecture may already exist privately, or may be close enough that capacity has to be built before the full public proof arrives. If a system can learn continuously, improve through use, and absorb real enterprise data, then today's chip orders and data centers could look early rather than excessive. That case does not require certainty. It requires believing the missing transition is near enough to finance in advance. Jevons paradox is the pattern where efficiency makes a resource cheaper to use, and total demand for that resource rises. In AI, cheaper inference could make companies use more computation because more tasks become affordable. That supports the bullish case for capacity. Better models may need fewer chips per task while creating far more tasks overall. The hard question is whether that expanded demand pays for the scale already being financed. History gives the best defense of building too much. Railway booms destroyed many investors and still left tracks, stations, timetables, and new economic geography behind. The internet bubble did something similar with fiber, data centers, protocols, and habits. A bubble can be financially destructive while leaving useful infrastructure. That possibility matters for AI. Even if valuations fall, some of the power, fiber, chips, and software discipline may remain useful afterward. Chapter 5. If the lake arrives. If continuous learning works, enterprise AI changes shape. The old promise that says, "We do not train on your data." That promise belongs to the frozen model era. It reassures customers that their private records will not be absorbed into the shared pond. A living system creates a harder trade. Its value comes from absorbing the specific world it inhabits: workflows, exceptions, customer history, documents, failures, and local judgment. The lake becomes valuable because its water is local. Distillation means training a smaller or separate model using the answers or behavior of a stronger model. In a future with continuous learning, value may move through many local systems. One company's model learns its own water. Another company's model learns different water. Capabilities can be distilled, shared, licensed, or traded without making every pond identical. The future data economy may look like many managed ponds exchanging fish, nutrients, and lessons under controlled access. The question is concrete. A lake-like AI would need to take an experience continuously, store useful memory, update its behavior, learn from consequences, and remain stable enough that the learning does not corrupt it. It would need to build internal models of the world and revise them through contact. It would need feedback that is richer than a star rating or a preference label. That is a demanding engineering target. Buying more electricity can support the search for it. Electricity alone is not the invention. Back in the living room, the child has already updated her model of the world: hardball, pain, beach ball, laughter. That intelligence runs on small power and ordinary food, but it was expensive to build. Years of care, and behind them hundreds of millions of years of evolution. Every version we know was shaped through ongoing exposure, consequence, adaptation, and time. The open question is whether our engineered ponds can become lakes through any route other than living with the world. The Koi Pond and the Lake, based on the essay by David Montgomery.